Hello and welcome to this pre-recorded event for International GCSE Physics. This feedback presentation will summarise the outcome of International GCSE Physics papers 1P and 2P. The papers were sat in May and June 2015. To help you get the most out of this feedback, you may want to have the following documents handy as we will refer to them during the session. Question papers for paper 1P and paper 2P, mark schemes for paper 1P and paper 2P, principal examiner's feedback for paper 1P and paper 2P. The presentation includes some extracts from these documents, but you may like to have the full versions for reference. It is possible that you already have copies of these, but if not, this is a good time to pause the presentation and download the documents. Similar documents from previous year's examinations are also available to download from the Edexcel website. These are the points that the presentation aims to cover. We shall be doing this in the context of student answers from this year's examination. Each paper is for the full range of levels from grade G to grade A star. The more able candidates should not be put off by the straightforward nature of the questions they meet in the early part of the papers. The grade boundaries for all subjects are published on the website at the same time that the grades are issued. This year's grade boundaries are shown here. The total mark for this paper is 120 and 2 hours are available, so the students could aim to gain a mark each minute. The examples shown in the next slides are actual student responses to the questions. They were collected as part of the examiner training exercise that is carried out before marking starts. This is the training that ensures that all marking is standardized. The paper began with a couple of straightforward multiple-choice questions. The students answered them well. These questions showed that 95% could identify fission correctly, and that 80% knew that the control rods absorb neutrons. Most of those who were mistaken about the control rods thought that the control rods just slow the neutrons down. In question 2A shown here, nearly all the students read the velocity correctly. But the second part of this section proved a little more difficult. About 70% realised that the bus was stationary for 10 seconds. Most of those who got this wrong added together all of the times for which there was no acceleration. They seemed to have a difficulty linking the idea of being stationary with a reading of 0 meters per second. In question 2B and question 2C, students need to recall the correct equation for many calculations. Calculating marks are broken down into a mark for substituting and a mark for evaluating the answer. Most students do this very well. Some had difficulty choosing the right unit for acceleration, though. Here is an excellent response to 2B. This student has recalled the correct equation, substituted properly, evaluated correctly, used the correct unit. So, full marks for this response, 4 out of 4. This student gave the wrong unit, but did everything else right. So the examiner gave 3 marks overall. Giving a velocity unit for the acceleration, as in this case, was a common error. I have annotated the examples with ticks to show where a mark is gained, and a cross to show where the response does not merit a mark. This student has recalled the correct equation, spoiled their calculation, but still used an acceptable unit. For this unit, the form meters per second was accepted, but meters per second squared is the preferred way to show this. Then, in 2C, the students were asked to calculate the average speed. This student has done well. The triangle mnemonic may have helped this student to recall the equation, and that is fine. However, the examiners are instructed to ignore triangles like this. They are not credited in the mark scheme. So the first mark here is given for the equation to the right, not for the triangle. More triangles to ignore here, and this version of the equation is acceptable. In this case, the student has overlooked the fact that total time should be used. So their average ignores the short time spent at rest. Just 1 mark for stating the correct equation. In question 2D, the students were asked to evaluate some data shown in the graph. There are 2 marks for this question, so the students should have spent about 2 minutes responding. The principal examiner feedback mentions that students can use the mark tariff and the amount of answer space given as a guide to help them plan their time. There are 4 lines for writing, so the examiner is not expecting more than a couple of ideas here. Some sample responses are included in Activity 1. You may wish to pause the presentation and download the file now. The exercise in the activity should take you no more than a few minutes. A commentary on the marking of each response is included at the end of the activity. The students can recall most equations and definitions well, but question 3b asks for a definition of alternating current. This is one of the few definitions that many students find difficult to get to grips with. The question and mark scheme are shown together on this slide. The ideas are important here. Students can express themselves in a variety of ways and still receive credit. There are lots of ways to get this right. Here are 2 correct responses. The first is very brief but clear enough. The second gives additional information. Both of these attempts get full marks. The sketch is not labelled, but is explained using the correct terms in the first sentence of the second response. These weak responses to the same question show confusion. The first one is not clear about the direction involved in this situation. The second confuses charge and current. Question 4 needs a longer answer because students are asked to discuss. The examiners saw many long lists without any discussion. This sort of response limits the maximum score to 3 out of the 6 marks. Only about half the students included some additional comment about the hazards they identified. Discussion points could be ways to minimize the hazard, consequences of the hazard, details of the physics involved. In some of the fuller responses, there was much repetition. Here are some responses to question 4. They are from 3 different students. The first describes a water hazard, marking point 1, and then goes on to say that water conducts and that this can cause an electric shock. The second identifies the hazard of tripping over cables, marking point 5, but gives no worthwhile amplification. The last one points out that electrical appliances can be misused, marking point 6, and describes how this, too, could cause an electric shock. (5a) is a practical question that tests experimental methods. The students were shown a photograph of the apparatus. About half of them were able to score at least 1 mark. Some sample responses are included in Activity 2. You may wish to pause the presentation and download the file now. The exercise in the activity should take you no more than a few minutes. A commentary on the marking of each response is included at the end of the activity. The students were asked to explain how this data had been handled. Most of them found it a difficult task. The examiners identified 4 useful ideas, and the students were expected to link any 2 of them, allowing for a variety of approaches. Less than half of the students were able to score any marks here. Students are generally well prepared for graph drawing, and marks were high for this part. Some did make the odd slip though. Where a poor scale was chosen, it usually involved some factor of 3, for instance, putting 3 centimetres as equivalent to 20 small squares. Many students did find it hard to interpret this unusual graph. A decreasing gap was measured in place of the more familiar increasing extension. Acceptable ideas for the interpretation included basic comments about the equal steps and a statement of Hooke's law. Question 6 was about magnetic fields. Some students drew field lines that crossed or mistook the direction of the field lines, but most did well with their bar magnet field. The good example shown here gets 2 marks. It was the same with the uniform field, and most scored well. 57% got full marks here. The weaker responses included typical errors like those shown here. The last 2 here each gained 1 mark for labelling the adjacent poles adequately. There was no penalty for the contradictory arrows shown in the second response. The energy calculations in both parts of question 7 yielded the expected good outcomes. A few students had difficulty with equating work done and energy gained in question 7a part 3. 75% scored at least a mark for the force diagram and 25% got full marks. The slide shows one of these. Question 7b part 4 proved harder. Most students did not realise that the velocity changed because there was an unbalanced force. In the past, questions similar to this one have caused difficulty. This time, however, the students seemed well prepared. The marks for 8b especially were excellent, with 70% getting 2 or more marks. Good responses were seen for other parts of the question, apart from 8e. Overlooking the stem led to some unfocused responses to 8e, particularly for 8e part 2. These responses were not related to the context of increasing height in the atmosphere. 2 examples, from different students, are shown here. There were some good answers to 8e, however. Both these responses, also from different students, scored the respective mark. Most students found it hard to describe the energy transfers here. Very few of them mentioned infrared radiation. 55% of the students scored no marks at all for this question. 30% gave responses worth 1 or 2 marks. Those who realised that the key to the question was the different emission from white and dark surfaces did best. For question 10, parts A and B were answered well. Nearly all students succeeded with the multiple choice item. 85% of students could give at least one similarity between Earth and Mars, but only 60% could offer a difference between the two planets. The calculation proved to be more difficult than expected. Students are given the equation on page 2 of the question paper. Some of them used an incorrect equation. Some students calculated correctly, but were unable to round their result to two significant figures. Students also found the last part of question 10 difficult. However, it was designed to be a harder question. Here are two good responses. Well done. Only 33% of students scored here. Responses to question 11 showed that most students know that gamma radiation exists as electromagnetic waves. Only 40% gained full marks for the half-life definition. Many were able to include time as an aspect of their response, for 1 mark. However, the idea of half of a time, see the first example here, was discounted. The third response here gets full marks. This student relates half-life to the activity, but relating it to the halving of an amount, for instance the amount of the radioactive isotope, would also have been fine. Many students were let down by poor examination technique when answering question 11b. The suggest command word means that they will need to synthesize their response from their existing knowledge. This is meant to be one of the more difficult questions. The availability of 2 marks means that the examiner will be expecting 2 linked ideas in the response. The context means that the radiation will need to pass through the patient. This, too, should be considered in the response. Less than 40% of students gained full marks here. Having struggled to define half-life earlier, few students were able to explain why the activity of a radioactive sample reduces with time. Only 20% gained full marks for question 11C Part 1. But most students could apply these concepts successfully. The half-life calculations were generally good, with 55% gaining full marks. The example shown is one of these. Question 12 showed that students find it hard to describe total internal reflection. Part 12a asks for meaning and shows that 2 marks are available. This should alert students to the fact that 2 ideas are needed in their response. Less than a quarter of students could make 2 of the 4 acceptable points. The responses to 12b were also disappointing. A third of the students could not give a single use for total internal reflection. "55% of the students gained full marks for this calculation. The example shown is an excellent response. Some confused the incident angle with the critical angle, calculated using sine of 25 degrees, and found a value of 2.3. Students should be aware of the context of their calculation. For most types of glass, refractive index is around 1.5. So, if a student gets a value for refractive index that is more than 2, or less than 1, it might be worth them rechecking their working. "80% of students scored at least 2 of the 3 marks available for Part 13a. An example of a good answer is shown. Wave properties are well understood. Question 13b asked for a non-standard method to determine the speed of sound. Many students made good attempts, and about 50% gained 3 or more marks. The lower scoring candidates rarely made mistakes in their method. Instead, they usually omitted further detail. Students may be familiar with an echo method or a microphone method. In both cases, the investigation hinges on the relationship between distance and a time. The next slide shows the mark scheme we used for this question. Students tend to respond well when asked to give a practical method, even when the context is unfamiliar. The slide shows the mark scheme for question 13b. The mark schemes used for this type of question are largely generic and would always include using a correct equation, mentioning repeating and averaging, or repeating and dealing with anomalies, stating the variable to be measured, which was the time interval in this case, other considerations that will improve the method. These other considerations should be related to the context set. For instance, consideration of the measuring instrument used, as in MP5. Consideration of the scale of a measurement, as in MP8. The students understand the relationship between wave speed, frequency, and wavelength. Over 80% gained full marks for this calculation. When the answer line gives SI units, it is often better to work in SI units from the outset. The mark for the unit conversion was lost in the example shown. There is no separate allowance for power of 10 errors in this case. Question 13D is an evaluation question. It was meant to be difficult. A mark was available for either of these ideas. MP1, the two waves travel at different speeds. MP2, the two waves travel the same distance in different times. Only 44% scored here, but most of these gave very clear responses. A lot of students tried hard but floundered here. Two of these weaker attempts are shown. The last question was designed to start at a fairly low level, but to get harder quite quickly. Most students were able to show how the voltmeter should be connected to the circuit. Fewer could give reasons for maintaining constant voltage or including the variable resistor. There were some good responses, however. These examples come from the work of 3 different students. The last part was meant to be difficult. The fictitious student mentioned in the question scenario makes a basic electronic thermometer. This student goes on to suggest that the current in milliamps gives a direct indication of temperature. The students sitting the paper were then asked to suggest reasons why this might be incorrect. Any 3 of 7 valid points were allowed. The groupings in the mark scheme do not denote any limitation. They are merely for the marker's convenience. Students did find the evaluation of this data difficult, but around 20% of students gained at least 2 of the 3 marks available. Here are some of the better responses. The marking points highlighted are MP6, line is curved. MP7, line does not pass through the origin. MP4, current not negative when the temperature is below 0 degrees C. We have completed paper 1P. The principal examiners made a general point about command words in their published feedback for both papers. Students should take note of the command word used in each question and use it as a guide to the amount of detail the examiner expects in the answer. For instance, whether to give a description or an explanation. A list of some command words is given in Activity 3. You may wish to pause the presentation and download the file now. The exercise in the activity should take you no more than a few minutes. Paper 2P is also for the full range of levels from Grade G to Grade A star, so the early questions tend to be fairly easy. The question paper is compiled using the same criteria as for Paper 1P, except that there are fewer marks and questions can draw on the entire subject content of the specification. Again, the examples shown are actual student responses to the questions. As is to be expected, nearly all students succeeded with the matching exercise in question 1. They are familiar with uses for electromagnetic waves, and 95% got this section right. Also, 80% chose the correct response for the multiple choice question about the electromagnetic waves from the sun. Students found question 1C difficult, and some of them made no attempt here, but most of the sketched rays showed the refraction correctly. There was some uncertainty as to the position of the IR ray. These examples all show correct refraction. The third example is the only one to show the infrared ray in the right position relative to blue and yellow light. Question 2 was about electrical power and household circuits. The multiple choice question was done well by the majority of students. A common error was to pick the volt definition joule per coulomb instead of the correct joule per second. Most students showed that they can recall equations and calculate with confidence. Where marks were lost, it was because the working was not displayed. The calculation asked for a demonstration. The command was, "Show that." These are some of the student responses. The first example is fine and gets full marks. The correct calculation yields a value shown to at least two significant figures, 4.17 amps in this case. This approximates to 4 amps, which completes the demonstration. The question asks, show that the current is about 4 amps, not show that the current is 4 amps. The second example attempts a demonstration but goes straight to the approximate value without demonstrating why it is approximate. So 1 mark only. The third example is a reverse argument. It starts with an assumption that the current is 4 amps. This is a valid argument, but does not answer the question directly. Only 1 mark was available for this approach. Question 2b asks for an explanation. This is the mark scheme. It is slightly simplified to fit it onto the slide. Markers would reward these ideas expressed correctly in different terms. For instance, ground for earth, current surge for a large current, melts for blows, etc. The students were well prepared and their responses were good, with 75% of them making 2 or more points. Weaker answers showed confusion and often dealt with the fusing and earthing as separate issues, rather than as component parts of a linked mechanism. The weakest responses mentioned electrostatics. Presumably, this was triggered by the idea of earthing. The last part of this question asked for students to devise an investigation. Responses were good, with more than 60% of students making 2 or more points. This is a situation where a good diagram can help the student's answer. The next slide gives an example of this. The student gains all 3 marks for a full response. The ammeter and variable resistor are both shown in the diagram. Both are referred to again in the text. Appearance in either diagram or text would have been sufficient for the marks. Spelling errors, such as in ammeter, can be ignored, provided the intention is clear. "70% of students gained at least 2 of the 3 marks available for question 3. The command word confirmed that just a simple description of the changing force was required for 3B. For example, force X decreases to 0. A full explanation was not required. Question 4 was about an investigation into the way water drains out of a barrel. When answering, students should be aware of this context. Stop clocks or stopwatches are fine for measuring intervals of a minute. The choice of instrument for measuring distance must also take account of context. Here, we are measuring 0.86 meters depth of water. A meter rule is fine. It meets the criteria for length and rigidity. Question 4B asked students to plot a graph from scratch. 66% of students gained full marks for this task. Well done, there were many excellently drawn curves. The examiners also saw some weak lines that lost a plotting mark, like this one, but just as many marks were lost for omitting the unit labels, or for using M instead of minutes. The final parts of the question asked students to consider the results of the investigation. Most students gained 2 of the 3 marks available. Responses to 4B Part 2 were often incomplete. The student realized that depth decreased with time, but provided no further detail. Simple comments, such as "the relationship is non-linear," would have sufficed. Some students did give thorough answers that included the idea of a changing rate. More than 90% of the students scored full marks for question 5A. Well done. Here is an example of one of those good responses. It would have been nice if the student had thought to correct their value to 3.0 kilogram meters per second, but 3-figure precision was acceptable on this occasion. The mark scheme for question 5B offered 2 alternative paths for the explanation. The momentum route, shown here, was the least favoured. It tended to yield weaker responses in this particular context. Some students omitted to mention that momentum is conserved, for instance. This Newton's third law route was the more favoured, and it tended to yield the stronger responses in this context. The curly brackets in MP1 surround the alternative acceptable phrases. Students who chose this route seem to answer more confidently. Overall, the students, regardless of the route chosen, ended up in 4 more or less equal populations, each scoring 0, 1, 2, and 3 marks for this question. Here is a good response that scores 3 marks using the second route. The marking points here are MP1, mention of Newton's third law. MP3, equal and opposite. MP2, forces on skater and snowball. The examiners allowed push as equivalent to force on this occasion. The rest of the vocabulary used in this response is well up to standard. For a full explanation of the award of marks for question 5C, it is better to look at the mark scheme document. This question was a bit harder than 5B. The outcomes were similar, but the proportion of 0 marks was slightly larger in 5C. Most students styled their response on those given in past paper questions, for instance, for questions about crumple zones. The main criticism from the principal examiners was about the unscientific vocabulary used. For instance, introducing the idea of time slowing down in place of increased time of collision. The time sequence of the context forced the harder explanation to the start of the question. The explanation of charging by friction in question 6A proved difficult in this context. Marks were spread fairly evenly, with half the students scoring 2 or more marks. The weakness of many responses to Part 6A can largely be attributed to omitting mention of insulators and/or the movement of electrons. However, the students rallied and 79% gave a fully correct answer to Part 6B, with many good explanations of electrostatic attraction. More than 80% of the students completed the decay equation in 7A correctly. The 2 marks were given separately for correct completion of the top and the bottom lines. Most errors came from a mistaken proton number for the alpha particle. Nearly as many students gave a clear reason why the camera is safe to use. However, only some of them linked a type of radiation to the absorption. For instance, aluminium absorbs radiation, instead of the aluminium absorbs the beta particles. Students can help their response by looking at the mark tally for the question. Here, 2 marks are offered, so the expectation is that 2 ideas will be included in the answer. Most students could give a general response regarding the dangers of radioactivity, such as risk of cancer or blindness. However, few went on to examine the context of the situation. An astronomer will place an eye close to the eyepiece and then remain in that position for a long time. Proximity and time of exposure both contribute to the risk. There were some good responses to this question. 25% of them were like this one, which is worth 2 marks. Here, the student identifies a danger, cell mutation or cancer. The idea of a close range is also given. Most students started question 8 well. They nearly all identified the step-down transformer. However, few explanations of the transformer core were successful. Unsuccessful explanations were usually based on the idea that the core would simply strengthen the field. These students seemed to confuse the transformer and the electromagnet. So, just 40% of the responses mentioned that the soft iron core could be demagnetized quickly. Only a handful of these students went on to mention the idea of the field changing or alternating. Some typical responses to question 8A are shown on this slide. Responses gaining full credit were rarely seen. Few students made the point that the field in the transformer core must be able to change or alternate. Some of the students did not pay proper attention to the context of this question. Many of the wrong answers showed 763 volts. A voltage as high as 760 volts is unlikely to be used when charging a toothbrush battery. An answer of this magnitude should provoke the student into checking their work. In the example shown, it is reasonable to assume that the student realized this initial mistake and then made a correction. It is also good practice to check through calculations and written answers if there is time at the end of the examination. Crossing through the original solution and replacing it like this shows the student's intention clearly enough. Full marks. About 75% of students gained at least 1 mark for the explanation. Many provided a full explanation like the ones shown. The pulse frequency calculation in question 8C Part 2 proved more difficult. This slide also shows an example of a good response to 8C Part 2. The students were asked to do quite a lot here. They needed to convert milliseconds to seconds. Most did this before substituting in the equation. This particular equation is one of those provided on page 2 of the question paper. Students are not required to remember this one. Lastly, the values were chosen so as to give students a chance to show off their rounding skills. So, careless rounding could lose a mark here. The examiners ensured that an incorrect unit conversion did not preclude the possibility of a mark for calculating. We have completed paper 2P. If you would like more information on statistics and grade boundaries, it is available from the website. GCSE English subjects and maths are changing first for first teaching in September 2015, with first assessments in summer 2017. GCEs for a range of subjects are changing for first teaching in September 2015, with first assessments in summer 2017. We have just published our specifications on the Edexcel website. They have been published early in draft form to enable teachers to have early sight of our proposed approach. We are also running a series of launch events. Our draft specs and SAMs, as well as further information about our launch events, can be found on edexcel.com. Other GCSE and GCE subjects following in 2016 and 2017. We constantly look to improve the delivery of our training and appreciate all delegate feedback. You will soon receive an email directing you to our online feedback form.